Hello, everybody. I'm going to go through the solutions of the question 120 in calculus section. Is about the mean value theorem. That's for the course Math1151. And that's at University of New South Wales. Okay, in this question, we are going to use the mean value theorem. Let's remind ourselves what was the mean value theorem and what it says to us. Suppose f is a continuous function on the interval a and b, and it is differentiable on the open interval a and b, so we are not considering the endpoints for the differentiability. And there existed this one real number such that derivative at c is equal to fb minus fa divided by b minus a. So this here is a slope of the line passing through the point fb and fa. So this is because the derivation of a function is defined as a slope. So this is the slope of the function, slope of the tangent of the function at the point. So this theorem says that there exists a point in this interval such that the slope of slope of the tangent at the point C is equal to is the slope of the line passing through the point FB and FA. Let's figure out C visually, geometrically what it is. So we have assumed that we have an interval A and B, and assume we have some FA and FB. Of course, this could be other way around. So we are concentrating on this rectangular band. We are drawing a line from FA to FB. So this is for A, this is FA. For B, this is FB. So we are drawing a line from this point to this point. And then that is the point AFA. This is the point BFB. And we are drawing a line. So basically, I should have said actually here, passing through a point AFA and BFB. So I'm thinking about this in two-dimensional space. And this theorem says that there exists some point such that the tangent at that point is parallel to this line. If you might have one curve like that, or you might have one curve like that, but I just draw some random curves in this rectangular band. So whichever the curve that I am doing up and down curves, I will always have a point such that the tangent line will be parallel to that line. In this case, I have many C's, as you see here. This is one C, this is another C, this is another C. All these up and down. We have up and down, and we have another one here as well. I haven't drawn. We have another one here as well. There's another up and down. So for all these up and down points, there exists like a tipping point here, which will be the tangent in that point will be parallel to the line here. The mean value theorem says that existed at this one. It might be more. Now let's try to use this and have a look and prove that some of the inequality holds. This is our aim. Okay. So we want, using the mean value theorem, prove these inequalities. Let's start. Let ft be ln(t) on the interval AB, AX. F is defined as continuous on AX. A is bigger than 0. F is differentiable AX because ln function is differentiable. ln function is continuous. So These two are conditions are satisfied, assumptions are satisfied. So if satisfies the conditions of a mean value theorem, assumptions of the mean value theorem, then we can use the mean value theorem. So this is an important step. So you have to check, you have to justify why you can use a theorem, any theorem. For this particular questions, we look at the conditions for mean value theorem, and it is satisfied, then we can use the mean value theorem. There exists at least one real number in this interval satisfying this condition. Slope of the tangent at the point is equal to the slope of the point x fx a fa. Okay, so what is the derivative of the ln function is 1 over c. That is why we have here. And this left-hand side, we have ln x minus ln a, x minus a. And ln x minus ln a, we know that that is ln x minus x over a. This is a general knowledge with the general fact with the ln function, as we know. So since c is in this interval, we have an inequality. A is smaller than c, is smaller than x. Now flipping around, it will make the smaller sign is bigger sign. Change the direction. We have 1 over a bigger than 1 over c, bigger than 1 over x. So by using this inequality for this case, so we have c here, right? This c is interval of 1 over a, 1 over x. So if you put x that one, that will be x minus a over x will be smaller than or equal to ln x over a. That will be the lower bound. For this upper bound, we will have x minus a over x. As required, we found the inequality that we would like to find out. Okay. For this, another one. In this case, we have the tangent here. Let's say ft is the tangent t. X is bigger than 0. Now focus on the interval 0x. Tangent inverse function is a continuous function and it's differentiable function. This is a general knowledge. Generally, we know that as a definition. As we are working on the tangent function, we already know that. And it is differentiable between 0 and x for every real number. It is differentiable. And if satisfies in the assumption of the mean value theorem, these two were the assumptions of the mean value theorem, then we can use the mean value theorem. There exists at least one c in the interval such that the slope of the tangent at the c is the slope of x fx 0 f0. Now, what is the inverse? We need to calculate the derivation of the tangent inverse function. Let's remind ourselves what was it. Tangent inverse t dt, derivation will be 1 over 1 plus t squared. And we also need f0, which is tangent inverse 0. Tangent inverse 0 is 0. And plug those, substitute those ones into here. We have 1 over 1 plus c squared as the derivative at c. And we have tangent inverse x minus 0, because tangent inverse 0 is 0. Then we have x only. Now we will, c is between in this interval. So we will look at how we can write this as an interval. So we multiply this by x because this is, we want to find out this inequality. So we multiply by x. We have x divided by x bigger than 0. X, we can. There is no ambiguity. If we can't do that, if x is 0, it is impossible. It is not defined. So x bigger than 0, it allows us to multiply. Then we have x here. So for this part, c is between 0 and x. On the denominator, we have 1 plus c squared. So multiply everywhere, take the square and add 1. Then we have 1 smaller than c plus squared plus x squared. Now we need, this is in the denominator, so we need to flip over. then the direction of this smaller than equal to sign will be reversed. It will be bigger than equal to sign. So that's 1. That's 1 over 1 plus e squared. It will be 1 over 1 plus x squared. So this will be the lower bound, and this will be the upper bound. And multiplying by x will give us the inequality that we are looking for. Okay, well, how about the last part of this question? Is a similar thing. The trick part is to choose the function. So this one is the function that we would like to choose. So ft is equal to 1 plus t. This is the function. And we are taking the interval 0 to 6. So we know this function is a polynomial. It is continuous, defined on 0x for all real numbers, x bigger than 0. And f is differentiable on the open interval for all x in the real numbers, positive real numbers. Then these two conditions means that f is satisfies the assumption of the mean value theorem. And then we can apply the mean value theorem. At least there exists at least one c, one real number between 0 and x, satisfying the condition, this condition. F prime c, what is the derivative of this function and c? So this is 1 plus t. If you take with derivative, this will be 1 over 2, because the power is 1 over 2. The power goes to the front, and then the 1 over 2 minus 1, that will be minus 1 over 2. So that's the derivative. Inside the derivative is just 1. Even though you're applying the chain rule here, chain rule will not add anything into the result. F0 we need to calculate here. We have F0. If you put t is equal to 0, F0 is equal to root 1, which is 1. Putting those things into here, we will have 1 over 2 root 1 plus c for this part. For this part, we have root 1 plus x. F0 is 1, so this is minus, so x, and 0 is 0. Take this 0, take this x into other side and takes 1 on the other side. Multiplying by x, we can do that. X is any positive real number. Then take this one on the other side. We will find this one. And now we are considering the boundaries of the c, the real number c. And we are looking here, the denominator is the square root of 1 plus c. So we would like to find some boundary of 1 over root of 1 plus c. That's what our aim. C is between 0 and x. Add 1 on all sides, and then take square roots. And then flipping over will change the direction of the smaller than equal to the bigger than equal to. So this will be give us the boundaries of 1 over root 1 plus c. Now, by using the boundaries of this term, which is this term here, we substitute these values into here as boundaries. We have lower boundary. Lower boundary is about this one. So it is just, instead of the 1 plus c, we will have 1 plus x. So this is why we have this 1 plus 1. This is our function. And we have on the right-hand side, we have 1, which is, this is 1. And that one is this 1. And then we have x, and then we have 2. And then the square root will be 1 plus c. 1 plus c times 1, it will be just x over 2. So on here, we have 1. From here, we have x over 2. It's exactly the same. This is the one that we would like to prove. And that's what we've done. It is the key idea for this question, as you realize, is to practice that you need to check the assumptions of the theorem in order to be able to use it. Right? That's the key output, key things to get from this question. I think that's all for this part. Yeah, thank you very much. Thank you.